Hello everyone, welcome to the video lecture series of the subject name VLSI Technology, and the subject code is KEC 053. So in the last lecture we have started the deposition process. So after the photolithography and the etching process, the next step is we have to deposit some of the material which can work as a gate or any other protecting layer for the further steps, right? So, the very first material which we are going to deposit is the polysilicon, right? So, in this lecture we are going to study the various materials like polysilicon, then silicon dioxide and silicon nitride. All these materials we are going to study that what are the reactions which are used to form the for the formation of these materials, and what are the temperature range, pressure range, and what are the reactors which can be the process reactors used for the deposition process. So the very first material here is the polysilicon. Polysilicon is deposited by pyrolyzing silane. Okay, so this is the pyrolyzing silane. It is deposited by pyrolyzing silane with a temperature range between 575 degree and 650 degree C, and this reaction is carried out at a very much low pressure, right? So we can see in the reaction that when your silane it is reacted in a proper environment at a very low pressure, we are going to have the silicon which will be polysilicon and hydrogen gas as a residual. Okay, so either pure silane or 20 to 30% silane which is blended in nitrogen gas can be used in LPCVD system with a pressure range of 0.2 to 1 torr. So for this process we can either use the pure silane or we can use the silane which is mixed with the nitrogen with a 20 to 30% at a very low pressure. Okay, so the practical use of this deposition, this deposition process is carried out for about 10 to 20 for nanometer per minute, and the properties of this LPCVD polysilicon films are determined by the deposition process pressure. At what pressure we are going to deposit the polysilicon, the silane concentration, how much is the silane concentration we are taking, how much nitrogen is blended in this. So all these factors are going to affect the properties of the deposited polysilicon. The next parameter, it could be deposition temperature and the dopant content. Amorphous silicon can be prepared by glow discharge decomposition of silane, and the various process parameters such as deposition rate are affected by the deposition variables such as total pressure. We have already seen in the last slide also, deposition pressure, reactant partial pressure, discharge frequency, power, electrode material, gas species, and reactor geometry, as well as it is also dependent on pumping speed, electrode spacing, how much electrode is spaced to create a glow discharge, right, and the deposition temperature. So all these parameters are going to affect the deposition rate, that how fast your deposition process will be carried out, right. So the higher the deposition temperature and RF power, the higher will be the deposition rate. This polysilicon can be doped with the another dopants, for example like phosphine, arsine, or diborane to the reactants, and this doping is done in situ environment, right? In situ environment means inside the chamber only. Okay, so this doping of polysilicon is done to vary the resistivity of polysilicon. Okay, so doping is done to vary the resistivity of polysilicon. That is why we can dope these dopants in the polysilicon, and each dopant will have a different effect on the polysilicon. For example, adding diborane will cause the large increase in deposition rate because the diborane forms the borane radicals named as BH3 that work as a catalyst gas phase reaction and will increase the deposition rate. Second, if you add phosphine or arsenine arsine, it will cause the rapid reduction in the deposition rate, because phosphine or arsine are the strongly absorbed on the silicon substrate, right? So that is why when we dope polysilicon with these phosphine or arsine, the deposition rate will be decreased, and thereby we will have the dissociative chemisorption of silane. And despite of the poor thickness uniformity across the wafer, when dopants are incorporated inside the substrate, the uniformity can be maintained by controlling precisely the flow of reactant gases around the sample. So if you control the reactant gases inside the chamber, the doping will be very much uniform. So in this slide we can see that this doping, when it is done at different temperatures or with the different processes, we can have the different types of graphs. This graph is made to show the resistivity of the phosphorus doped polysilicon. Okay, this polysilicon can also be doped independently by some another method. Here we can see that, and this polysilicon doped with phosphorus diffusion or ion implantation, or it is done by in situ doping. The resistivity is observed. We can see here that if your polysilicon is doped by phosphorus, if it is carried out with the diffusion process, right? With the diffusion process, we have this much resistivity, right? It varies between 10 raised to the power minus 2 to 10 raised to the power minus 4, right? Somewhere around 10 raised to the power minus 3 around, right? So if this doping is done with the help of ion implantation process, so see your with the variation in temperature, we can see that your resistivity is decreased, right? And here, if your phosphorus doping in polysilicon is done in situ environment, we can here see that we have a very sharp degradation of resistivity if you increase the temperature, right? So this way, if you decrease the temperature, right? So this way we are going to see, we have seen that the resistivity not only is affected by the dopant, it is also affected by the process parameter, the process in which we are going to dope the phosphorus. So this polysilicon can be oxidized in dry oxygen at temperature between 900 to 1000 degrees C to form the insulator between the doped polysilicon gate and another conducting layer, right? So and the resulting material, that is your semi insulating polysilicon, which is named as SiPOS, is also used as a passivation layer to coat the high voltage devices. The next material which we are going to study for this deposition is silicon dioxide, right? Each material will have the different application. For example, this in the previous slide we were studying the polysilicon, right? This polysilicon, we know that when we fabricate the MOSFET, right? When we fabricate the MOSFET, we have this oxide layer. Just a minute. Right, we have this oxide layer. We have this N plus doping in the p-type substrate, right? We have this oxide layer, and over that polysilicon is deposited, which is used to form the gate material. This is the polysilicon, right? So polysilicon is mainly used for the formation of gate materials, and sometimes it is used as a passivating layer for the high voltage devices. So each material will have the different properties and will be used for the different applications. So next material which we are going to study is the silicon dioxide. So several deposition methods are used to produce the silicon dioxide, and the film can be deposited at a temperature lower than 500 degrees C by reacting the silane. It is done by reacting the silane with some dopants, phosphorus. In this example, we are taking the phosphorus and oxygen under the reduced pressure or atmospheric pressure. So silane, when it is reacted with oxygen, we are going to have silicon dioxide and hydrogen gas as a residual gas. When phosphine, it is reacted with hydrogen, we are going to have P2O5, with 6 times of hydrogen. So this process is conducted in a APCVD reactor or LPCVD reactor chamber. These reactor chamber we have studied in the previous class. If you have not gone through those reactor chamber details, you can check the previous lecture. The main advantage of the silane oxygen reaction is that the deposition is carried out at a very low temperature. At a very low temperature, we are going to carry out the reaction, and the deposition will be done at a very low temperature, and it will be deposited over the aluminum in the metallization process. So, and the primary disadvantage for this process is we can have the step coverage will be very much less. We have the disturbed step coverage. High practical contamination will be there because of the loosely adhering deposit materials on the reactor walls, right? We have seen in the reactor chambers also that in case of hot wall reactor chambers, especially in case of hot wall reactor chambers, right, we may have some dopants which are flying inside the reactor chamber. They may go and sit on the substrate, so they will finally lead to the contamination. Okay, so this silicon dioxide can be deposited at the temperature range of 650 degrees C to 750 degrees C in LPCVD reactor by pyrosilane tetraethoxysilane with the name SiOC2H54. This compound is abbreviated as TEOS, and it is vaporized to have that in the liquid form, and the reaction is this TEOS. Okay, when it is reacted, we are going to have silicon dioxide and some byproducts. So the byproducts can be organic or organosilicon compounds. The LPCVD TEOS is often deposit the spacer beside the polysilicon gate. It is used to provide as a spacers along with the polysilicon gate. The process offers a good uniformity and the step coverage, but a slightly higher temperature limits its application on the aluminum interconnects. Okay, so for the interconnects we are not going to use this process so that we can have the spacer. For that we are going to have some another process. The silicon dioxide can be deposited by LPCVD at about 900 degrees C by reacting the dichlorosilane with the nitrous oxide. So when this TEOS is reacted with nitrogen oxide, we are going to have silicon dioxide, nitrogen gas, and HCl gas is a reaction product, right? This HCl gas is a very much toxic gas. This deposition technique provides excellent uniformity, and this LPCVD TEOS, it is employed to deposit as an insulating layer over polysilicon. So this over this polysilicon layer, it used as a insulating layer so that we can protect our gate terminals from the next processing steps. This plasma assisted CVD requires the control and optimization of the RF part density, frequency, and the duty cycle. In addition to the condition, it is similar to those as we use in the LPCVD, such as gas composition, flow rate, deposition temperature, and pressure. So in this also we are going to your deposition process is affected by these gas composition, flow rate, deposition temperature, and the pressure as well as. And in case of this LPCVD process, when it is carried out at low temperature, the PECVD process, it is a surface limited reaction, and the adequate substrate temperature control is thus necessary to ensure that we are going to have a very much precise thickness of dopants which are going to be deposited over the required substrate. So by reacting silane and oxygen or nitrous oxide in plasma, silicon dioxide film can be formed by this following reaction. When this silane it is reacted with oxygen, we are going to have the silicon dioxide and hydrogen gas as a reactant. And when this silane is reacted with nitrous oxide, we are going to have silicon dioxide, which will be deposited over the given required material, then nitrogen gas and water molecules as a residual products. The last material which is very much important in case of this VLSI is the silicon nitride. Stoichiometric silicon nitride Si3N4, it can be deposited at certain high temperature as compared to your previous two materials, that is done at 700 to 800 degrees C at atmospheric pressure. So when this silane is reacted with NH3, we are going to have this silicon nitride and hydrogen gas as a residual. And using this LPCVD, this silicon nitride can be produced by reacting dichlorosilane and ammonia at the temperature between 700 and 800 degrees C. So all these reactions are very much controlled, temperature controlled. If you vary the temperature even at 705 degree, we are going to see that the layer of deposition is not up to our requirement. It will be changed. Either it will be decreased or it will be increased. We have to see that, right? So this temperature, it is reduced to 695. Right, we have the variation. So if you reduce that to 695, even we can see the change in the thickness. The reduced pressure technique has the advantage of yielding good uniformity and higher wafer throughput. And hydrogenated silicon nitride films can be deposited by reacting the silane and ammonia or nitrogen in plasma at reduced temperature. So we can see in the reaction that when the silane is reacted with NH3 gas, we are going to have silicon, SiN, H and hydrogen gas. When it is again reacted with nitrogen, we are going to have silicon nitride and hydrogen gas. So this plasma assisted deposited films, they will give you a good yield at a low temperature by reacting the gases in a glow discharge, in a plasma discharge. Right? We have already know that the plasma is created when your gas is kept at a very much low temperature and the required pressure, then it will create a plasma. So two plasma deposited material, that is plasma deposited silicon nitride SiNH and the plasma deposited silicon dioxide are very much useful in VLSI and ULSI technology. So when you go down in the dimension size, when you reduce the size of the device, this deposition is very much important. The thickness of the deposited material, it should be very much precise. So on account of the low deposition temperature, it is carried out at 300 to 350 degrees C. This plasma nitrate can be deposited all over the final device metallization. Okay, so this silicon nitride is specially introduced before the metallization process when the final metallization is done, so that when you diffuse the metal lines, when you plant the metal lines, because the metallization is also a process which will be carried out at a very much high temperature, right? So that aluminum, copper, whichever the metal lines we are going to use, whether it is aluminum, copper, silver, gold, tungsten or titanium, that material should not diffuse inside the substrate. So these silicon nitride films, silicon dioxide films, they are all used as a protecting layer for those metal lines. They will protect the substrate from the metal lines at high temperature. So this plasma deposited films contain a large amount of hydrogen, that is between 10 to 35 atomic percentage. This hydrogen is bonded to silicon and to nitrogen also, and as well as silicon, water molecules and H2O. And we can see in the next table that for these processes, for each composition, we are going to have we are going to have each composition will be different. For example, the deposition when it is carried out in a LPCVD reactor and when it is carried out in a plasma reactor, the temperature range is here 700 degree to 800 degree C. Okay, and here we are going to have the temperature range 250 degree C to 350 degree C, right? The composition we are going to use for the silicon nitride is Si3Na N4H, and here we are in the plasma we are going to have SiNH. It could be N2H3 depending upon the requirement. This silicon nitrogen ratio, it varies. For LPCVD we are going to have 0.75 and for plasma it will be 0.8 to 1.25. Atomic percentage we are going to have here 4 to 8, here we are going to have a very large percentage, atomic percentage. Refractive index is almost same, that is 2.01, and here it lies between 1.8 to 2.5. And here we can also compare the density, dielectric constant, resistivity we can see that with the help of LPCVD we are going to have 10 raised to the power 16. Right, and in with the plasma we are almost going to have the same resistivity. Dielectric strength, here we are going to have more dielectric strength as compared to your plasma assisted deposited materials. Energy gap here almost same, the stress will be 10 T, or here we can have the 2C to 5T. Okay, so we can see that to have the almost same results, but the temperature variation is very much there, right? Your LPCVD process is carried out at high temperature, whereas the plasma assistant is carried out at deposited material is carried out at a very much low temperature. The last is your rapid thermal chemical vapor deposition. In case of rapid thermal chemical deposition, it is used as a process so that we can have a single wafer, we can have the deposition over a single wafer, right? So for this it is a well suited technology for a single wafer cluster tool technology. A typical design for RT CVD we will be showing here, and the chamber walls are water cooled. Here we can let us see this diagram first. It is the RP CVD reaction chamber. Here we have the vacuum pump which is used to create the required vacuum inside the chamber, right? We are not going to use the simple mechanical pump, we are going to use a very much high precise pumps. It could be Cairo pumps or any other pumps. Your simple mechanical pumps use some oil diffusants inside them, right? So when those oil particles they may go inside the chamber and some contamination will be there, which will lead to the changes in the variation in the substrate properties, right, or in the deposition of this deposition properties, right. So for this vacuum pump we are going to use a very highly precised pump. Mechanical pumps will be used here, so which is used to create a certain pressure. Here we can see that we have this pump, some isolation valves will be there. It is the quartz window. Here we have the level controllers where we can use it can be used to control the deposition levels. Gas will be passed from this side, and here we have the water coolants. These are the water coolants, so that it will be maintained out at a cool temperature, at lower temperature from the outside. So this chamber walls are water cooled, thus eliminating the deposition on the chamber wall. So it is a kind of cold wall reactor, right? It is a cold wall reactor. If the walls of the reactors are cold, the contamination will be pasted to the walls only. It will not be in the free space. It will not be traveling around the substrate, and finally they don't get pasted over. They don't get mixed with the deposition gases and won't be deposited with the deposited material. So this RT-CVD requires a high temperature but shorter time to deposit the same material as compared to your LP-CVD process. So this leads to a very good advantage that your deposition time is here reduced. So furthermore, this temperature is the switch that turns the RTP deposition process on and off, avoiding the long ramp up and ramp down time which requires in the conventional method. So to be commercially viable RT-CVD system, it must be available to a process with a single wafer in 1 to 2 minutes. For this, with the help of this process, your single wafer will be processed in 1 to 2 minutes with the giving a corresponding throughput of 30 to 60 wafers per hour. And for relatively thick deposit of film, that is your 100 to 200 nanometer, it requires the deposition rate, it should be greater than 100 nanometer per minute. And in comparison, the typical deposition rate in case of LP-CVD was your only 10 nanometer per meter. So your deposition rate is increased, throughput is increased with the help of this single wafer reactor chamber. So these are the this is the reaction which we are going to use in this RT-CVD reactor. When this TEOS is reacted, we are going to have the silicon dioxide, water molecules and C2H4. These are the some another reactions which are going which are used to deposit the silicon dioxide and silicon nitride. This silane, when it is reacted with oxygen, we are going to have silicon dioxide. Silane, when it is reacted with nitrous oxide, we are going to have silicon dioxide. When SiH2Cl2 it is reacted with NH3, we are going to have silicon nitride. When silane it is reacted with NH3, silicon nitride we are going to deposit. And then when this silane it is reacted into the environment, we are going to have simple polysilicon material. Okay, and hydrogen gas as a residual element. So in this lecture we have studied the deposition materials, which are the materials which we are going to deposit for the various application, right? So we have seen that polysilicon is generally used as an insulating material and it is used as a gate material, right? It is used as an insulating material because we never want your gate current to be entered inside the substrate, right? So that is why it is known as an insulating material or gate material. Second, silicon dioxide, silicon nitride. Silicon nitride is generally used before metallization process so that your metal lines, they should not diffuse inside the substrate, okay, or they don't get mixed with the substrate. So to protect the substrate from the at the higher level, at the higher temperature and for the further processes, we are going to deposit these layers. Okay, so we have covered the crystal formation. We have seen the crystal. We have seen the crystals, how the crystal behaves. We have with the help of CZ process, we have created a wafer. Over that wafer, with the help of epitaxial process, a layer is generated which will work as a support material. Then we have the oxidation. We have seen the oxidation which is used to deposit the SiO2, right? Then we have seen the photolithography. Right, we have seen the photolithography process. After photolithography process, with the help of etching, some windows will be created where we are going to deposit some, we are going to diffuse some of the atoms, dopants, and after that we have here seen the deposition, right? So deposition is done before the diffusion so that we can, your layers are protected for the further processes. So in the next upcoming lectures, we are going to study the diffusion process which is used to implant the N plus and P plus impurities. Then ion implantation we are going to study, and finally how the metallization will be done and how the packaging will be done. Thank you so much for today's lecture.